We've already seen how the potential for aliasing can be an optimization blocker. And by aliasing, we mean two pointers pointing into overlapping memory. In this case, we have pointers A and B coming in, and we're looking into pointer A every time in a loop and writing to a pointer B. And if you look at the machine code generated for this inner loop here, then you see that every time around the loop we are storing into BI, even though it would make sense to take that storage into BI and lift it out of the for loop, right? Because we really don't care about the intermediate values of BI. But the compiler can't prove that we don't care about that, because it can't prove that we don't pass in A and B where B is a portion of A. So that changing B here as we go can change the results that we get out of A. So if we don't mean for this kind of thing to happen, we can help the compiler out and explicitly write some local variable s to accumulate the result of of walking over A in the inner loop here. So instead of writing to BI every time, we just write to s and then put s into BI at the very end. What this does is allow the compiler to allocate s in a register instead of on the stack. So it's not having to write into memory every time, it's just writing into registers, and it'll be more efficient. You can see the code that we get has to look into A every time, but it's just accumulating into RDI, which is eventually moved into BI. So sometimes the solution to help the compiler with aliasing is just to avoid looking through the pointers more than you need to. Another possibility is that you can be more precise with your types, and this will end up helping the compiler. So here we've got an example similar to our call F and G example, but this time it's with a separate array C. And it looks like A and C could be pointers to overlapping memory, so that we would have to look up A twice every time here. But if you compile this program and look at the machine code, what you'll see is we only look into A once. This is an address calculation that's really just multiplying by 2 the value that we looked up before, that's in R8. So in fact, the compiler is generating a single lookup into A and storing into C every time. So this, given all of our discussion before, this might be a little puzzling, because you could make an integer array and then make C be part of that. You'll notice that I have to put a cast here. That's because in this program I made A an integer pointer and C a pointer to longs. And it turns out that that is what enables the compiler to make this distinction. The term strict aliasing, which is something that C assumes, means that if you have two different types, int and long, then you almost certainly didn't mean for those to overlap. It's a kind of heuristic. The compiler and the C standard and the programmers all sort of agree that if we have pointers with different types, that is a way of saying I don't mean for A and C ever to alias, and so the programmer doesn't have to go further out of their way to distinguish those. We should be a little more careful here that there are some types that are considered to overlap. For example, void star. If you're looking into memory at a void star, then that counts the same as any other pointer. But well, you can't look at a void star, but you can look at char star, and char star for historical reasons also is treated equivalent. So if either A or C were a char star here, even if the other one is still int or long, then the compiler would not assume that they point to different parts of memory. And that's just because historically char star is used as a generic pointer to any sort of memory. Strict aliasing rule explains why something that we saw many videos ago didn't work, where we tried to have floating point number f, take its address, cast that to an int star, and look at it with the goal of looking at the bits of f in terms of integer bits instead of floating bits. The reason this doesn't work is because the compiler knows that f resides at some address, but it's a float pointer. That address corresponds to a float pointer, and an int pointer and a float pointer aren't supposed to point to the same thing. So it is free to either look inside the int pointer and then initialize the floating point value, or the other way around. On the other hand, if we use memcopy, this forces the compiler to fill in the 1.2 in the floating point number f, roughly because we give memcopy to we give it a void star, right? This gets coerced to void star, and void stars can overlap with floats, and so it's forced to fill this 1.2 in before it tries to copy it over into the memory for I. Right? More precisely, it's because the C standard directly specifies what memcopy does, but you can think about it this way to get to the same result. So with strict aliasing, the point is that you can get the compiler to make certain aliasing assumptions, or a lack of aliasing is when you're working with different types. And in practice, this is usually a pretty good rule, although sometimes it can be confusing when you really do mean to play tricks for looking at memory in different ways.